This episode of Astronomy Cast is brought to you by Swinburne Astronomy Online, the world's longest-running online astronomy degree program. Visit astronomy.swin.edu.au for more information.
Astronomy Cast, episode 86 for Monday, April 28th, 2008. The End of the Universe, Part 1, The End of the Solar System. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hello, Pamela.
Hey, Fraser, how's it going?
Well, this is going to be a sad one.
It is, but isn't astronomy all about death and destruction?
Well, I guess it is, isn't it? I mean, this is a show that we've wanted to do since we started Astronomy Cast, but we always thought it was a little too early. And I think we wanted all the listeners to know that we're very positive, happy people with, well-adjusted people with families that we love and love us. We have a great enthusiasm for astronomy and the future.
But now that it's spring and life is abounding everywhere, we decided to discuss death.
Exactly, the inevitable long-term destruction of everything that we all love forever. So, time to look at a grim look at what the future holds for the universe. So this week we're going to stay home and consider the end of humanity, the Earth, the Sun, and the entire solar system. And the next week we'll extend out to the very end of the universe and blow your minds. Now, if anyone wants a sneak peek, this is actually based on an article that I did at Universe Today called The End of Everything. But it is so fascinating that we wanted to go into it in great depth. So, Pamela, let's start talking about the end from the beginning. Let's start with the end of humanity.
Well, so the end of humanity you can look at as coming from a number of different things. There's always we could blow each other up tomorrow just because we can. We have the technology to do that. But hopefully the world political systems are a bit more stable than that. And then there's always we could unleash a super disease and wipe out all of humanity next year.
Asteroid? We could get hit by an asteroid?
We could get hit by an asteroid. There's all sorts of different wonderful ways we could die.
So, I mean, the end of humanity could happen in a blink.
In a blink.
Just but who's to say what's going to happen? There's no probabilities. This is the future. So, all right. Well, I think we can all imagine a bunch of awful ways that we could instantaneously or within a few hundred years end humanity as we know it. So we're not really going to deal with that. Let's talk about more of the inevitable stuff.
Well, statistically, we try and put predictions on how long can a species last. And one of the things we do is just because we can. We start from the basic statistical premise of, let's assume half of all the human beings that will ever exist have already existed, and that we're midway through our society's lifespan on this planet. And then project forward and say, okay, so if half have already existed, then we know how many are to come, and we know how fast we're reproducing, roughly. And that gives us about 10,000 more years on the planet Earth.
All right, so we've had 1 million years so far to get to where we are, and then another 10,000.
And we're gone.
And we're gone. But that doesn't seem very feasible to me, because population rates aren't going to necessarily increase forever. And if we can find some sustainable level, then we could last a lot longer.
And it's a purely statistical argument. And the truth is, we don't know what's going to destroy us. We don't know what's going to kill us. And so it could be that we're here up until the point that the planet can no longer sustain large life at all. And that gets us a little bit more time.
Right. And I think the other possibility is that we can always evolve or even technologically change ourselves into something else.
And we can always jump this solar system and go find someplace better to live. We're just not there yet.
Right. Now, when will the Earth stop being a nice place to live, and why?
Well, our sun Right now, we don't notice it so much. In fact, anyone who tries to say that global warming is caused by the sun, not so much in line with what scientists are saying. But long term, our sun is going to heat up. It is going to increase its energy output. It is going to make our planet warm up. And we're also going to run out of the ability to effectively cycle carbon in and out of our atmosphere. And so with the breakdown of the carbon cycle and with our slowly heating sun, in 1 billion years, water on our planet is toast and really can't live on the planet.
Now, why is the sun heating up?
It's part of its evolution. As it changes what it's burning, how it's burning in its core, it's going to get a little bit hotter, a little bit hotter, a little bit hotter, until it runs out of fuel in its core. It's stars on the main sequence. They don't just sit there and say, I'm going to burn hydrogen in my core at the exact same temperature for the next 10 billion years. But rather they go from, I'm going to start burning hydrogen, and they flare up and they do erratic things, and they eventually settle onto the main sequence. And while sitting on the main sequence, they slowly get a little bit warmer and a little bit warmer. It's just part of the natural evolution of running through the fuel in the core. As the chemical properties in the core change, as you build up more helium, as just the mix of elements changes, the sun's going to run a little bit hot.
And so where we stand right now is just a snapshot of the sun's temperature. It just happens to be that right now the temperature of the sun is very comfortable. But in like 500 million years, the sun will have gotten so hot to the point that the whole Earth will pretty much just be a desert.
Yeah.
And you can imagine the habitable zone around the sun, which we were nice right smack in the middle, is pushing outward with the Earth no longer in the middle and starting to kind of be on the inside of that habitable zone.
And this isn't to say that Mars is going to become a better place to live, because while the temperature situation on Mars is going to be a little bit better, Mars still doesn't have an atmosphere. So it's not that we can go there and be safe either. And Mars not only doesn't have an atmosphere, but doesn't have a magnetosphere. So even if we do jump ship and go to Mars, we still have problems with radiation to contend with.
Now, you said the oceans would be toast. So what's that process?
Well, as you warm up the planet, just increasing the temperature of the planet 50 degrees Celsius, you start running into massive evaporation. And once you get too much water vapor in the atmosphere, then you start a runaway greenhouse effect. And eventually, our oceans evaporate into the atmosphere. And just between normal collisions between particles, you're going to start losing some of the lighter elements away from our atmosphere. It's sort of like every time you lose a helium balloon, that's helium that's no longer part of our planet. We're eventually going to run out of helium. And other lighter elements are going to go away. So you evaporate the water, and if it breaks into H2 and O in the atmosphere, those H's are going to go away, and you lose the ability to make water.
And that's what's happened to Venus.
That's what happened to Venus.
Yeah. So that's the future. Now that is global warming.
That's definitely global warming. And that's the type of global warming we can't survive.
Right. And you look at the desert and you can see that no large creatures can really enjoy themselves. Things have to hide underground. Life doesn't flourish in the same way that it does in, say, a tropical rainforest or in the ocean. So then what does the future hold for life then?
Well, eventually it's going to start moving progressively more and more toward the poles. And we're going to end up with today's prairie creatures, today's desert creatures, eventually huddling around the North and South Pole. I don't know what they're going to be huddling on with the North Pole because there's no land there. So probably most of them will be combined to whatever can get itself to Antarctica somehow. And eventually, even there, they're going to run out of resources to keep themselves alive, and our planet is going to become a dead desert world.
So is that it? There will be no life on Earth whatsoever?
No intelligent life, no large life. I mean, who knows what bugs are going to be existing in the bottoms of coal mines someday? Who knows what will manage to find ways to survive underground? But large life doesn't exist well 7 miles under the surface of the planet.
No, but small life does. I mean, isn't there more? I've heard estimates that there's more microbial life under the surface of the Earth than there is on top of it.
And this is where you make the distinction between large life and microbes. Microbes could be just about anywhere. I've heard some microbiologists say, more microbes on and in your body than
Hmm.
human cells on and in your body.
Right. You're really just a colony of microbes. You're not a person. You know,
Something like
you're like
that.
their shell. Yeah.
We're a walking island for
A
bacteria.
robot. Yeah. An island. Yeah.
But where are the elephants going to go? Where are the wolves going to go? Where are the bats going to go? Sure, there might be mice living underground, but I can't imagine, and most of the research papers I looked at just don't see a future for large multi-celled individuals in the future. Our planet just won't have the resources to support them.
I think it's funny because people say, oh, 7.5 billion years from now, the sun's going to turn into a red giant. And we'll get to that in a second. And that's how long we have. But the reality is that we really only have about 500 million years. And that, I think, for people feels very different. I know they're both incomprehensibly large amounts of time. But when you look back at how long the Earth has been here for, say, 4.5 billion years, and you say, and large life really only has another 500 million years, that seems very shocking and very extra sad. You think you've got lots of time, but there isn't lots of time. Maybe only one shot at large life. This is it. Here we are. This is our chance to make large multicellular organisms happen. And then 500 million years from now, that's that.
Well, and part of what makes it so sad is as we look back over our own archaeological record, we can see, well, here's where the first man was found. Here's where the first plant was found. Here's where the first multicellular object was found. And you can only go back so far. But that distance that you can go back does incorporate millions of years. It doesn't incorporate billions of years for the multicellular things. Microbes first appeared about 3.5 billion years ago. But you can go back 500 million years and find a fossil record. When you say, life has 7.5 billion years to go, well, that's longer than the Earth has been around. That says we haven't reached the halfway point yet. We're not middle-aged yet as a planet with life. But when you say 500 million, that means that we're past the halfway mark. That means that we should be getting the black balloons at our planet's birthday party and signing up for planetary Medicare and Medicaid.
Right.
It's once you're past the halfway mark, there's something bittersweet.
Now, the sun, though, is continuing to get hotter and hotter. And so what does the future hold then for the sun?
Well, our sun, its total main sequence life, the amount of time that it's going to be happily burning hydrogen to helium in its core, it's about 11 billion years. And we've got, as you said, about 7.5 billion years to go. So once the sun runs out of hydrogen to burn in its core, it's going to end up burning a shell of hydrogen around that core. And in the process, it's going to bloat itself out, and it's going to become what we call a red giant star. And it's not too huge at this point. It's big, but the Earth is probably okay. Then it's going to go through other phases. It's going to actually ignite helium in its core, and it's going to become what we call a horizontal branch star. So it stays the red giant for about 1.3 billion years, and then it burns helium after that as a horizontal branch star for about 100 million years. And then it becomes what we call an asymptotic giant branch star, and I just love that word. And this is a star like what the Mira red variable stars are. And it only spends about 20 million years in this phase, but it's huge. And this is where we have to start worrying, because a lot of crazy stuff's going to be going on. The sun, as it gets old, it can't hold on to its atmosphere very well. And it's going to be blowing its atmosphere out. Before it dies, the sun is actually going to shrink to almost half of the size that it was when it was born. And as it's blasting this material out, the orbits of the planets are going to get a little bit bigger and a little bit bigger because they're not going to be held onto as tightly by the mass of the sun, which is diminishing. The sun's mass actually gets to be less mass. And so even though it's big, gravitationally, all we care about is where its center is and where the center of the Earth is. But when that mass gets less and less because of this mass loss, this wind that's blowing material out, that amount of mass yanking on the planet Earth, that gets less. And so we drift further and further away.
Right. I know in when you do articles about these giant red giants in this phase, they lose hundreds of times the mass of the Earth every year, and that has to have an effect with the total gravity of the star itself.
And so the question that people have been trying to answer is, so how does this tug of war between the Earth orbiting the sun and the sun losing its grip gravitationally as it loses its mass play out as it expands? Does the Earth move far enough away that we don't get eaten? Or does the Earth stay just close enough that we get consumed by the sun as it bloats itself out? And there's a lot of different conflicting papers. The two things that are so hard to understand are what amount of mass loss is going to take place and what sorts of things might affect the size of Earth's orbit. For instance, there could be tidal locking, where the Earth-Sun-Moon system gravitationally yanks onto one another, and the Earth's orbit gets slowed down until it's actually on a smaller orbit when you start taking into consideration things like angular momentum. And this tidal drag, this slowing down due to tidal effects, could shrink Earth's orbit just enough comparatively that we get eaten. And that's what some of the latest models are showing. But just a year ago, the models were showing, no, we're fine. So I think this is something that's not going to be settled for a long time, because really different stars do different things. And it's hard to predict exactly what our little star is going to choose to do.
But even if it survives, the amount of damage is just immense. I mean, the sun is gigantic. It's giving off tremendous amounts of heat. The Earth, maybe it survived, but it's not far away from the sun in the best case. It's inside the sun's envelope in the worst case.
Yeah, we're going to be that burnt biscuit that someone forgot to take out of the oven.
Right. Even that microbial life deep under the surface is going to be really wondering if it should have moved a long time ago.
And so the future for our planet is, well, we either get eaten, which could be kind of cool. Because you can imagine human beings have moved on somewhere else, and we're looking back at our sun, and the moment the Earth gets eaten, the sun chooses to do something kind of cool. That might be nice. Or it could be that we're left behind as a crispy nugget of former planet. And that can also be kind of cool. You can imagine future humans, should we choose to survive as a race, coming back through the solar system and pointing at the burnt out rock and going, that used to be the home of all humanity. Sort of like nowadays, you can walk through parts of England and Scotland and go, that rock used to be part of the Roman wall. The Roman wall's not really there so much in all the areas, but the rocks are.
Now, is there any way to prevent this?
No. It's a star.
Right, but I've heard, no, I guess you can't prevent the star itself, but is there a way to prevent the cooking of the planet?
Well,
I've heard like these solar system engineering projects, it might be possible.
There's always the idea that you go out, you grab yourself a whole bunch of metallic asteroids, and you mill them in space and make yourselves a giant sun shield. And that you might be able to prevent the planet from getting overheated and the oceans from evaporating. But once the star starts to get into the asymptotic giant branch phase and things like that, it's going to cool off, but it's blasting so much energy out that you have to wonder if there's enough asteroids out there to build a big enough solar shield to prevent our planet from getting crispied.
Now, didn't you say that there would be the habitable... I remember in a previous show, you'd said that the habitable zone would move out so far that places would start turning into liquid water.
Yeah.
Like moons of Jupiter and Saturn, right?
As the sun starts giving off significantly more luminosity, admittedly at much cooler temperatures, but its total output will increase as it goes and becomes a horizontal branch star. Yeah, we're going to start doing things like melting the moons of Jupiter, which is kind of cool to think about.
Except for Jupiter's terrible radiation. This is all hopeless. I mean, this is all pointless. I mean, it's funny how you search for little glimmers of hope, Like,
yeah, other solar systems.
All life will be destroyed. The oceans will have boiled away. The sun will have consumed Mercury and Venus and possibly the Earth. But maybe, just maybe,
we all go live on Titan.
Enceladus will, be be kind of
It'll
slushy.
melt. It'll be no
Right?
more.
Like, woohoo! All right. And how far will, and then what will happen to the sun?
Well, so eventually, the sun is going to become what's called a planetary nebula and a white dwarf. So what happens is the outer atmosphere of the star puffs off, floats away, becomes a pretty nebula, and the core of the star, the part that fused into helium, the part that perhaps fused into carbon, that inner core is going to be a white dwarf. And it's no longer going to be generating any of its own energy. It's just going to be sitting there going, I'm hot. Wait, I'm not hot anymore. I'm getting cold.
Right. The star has ceased fusion, and now whatever is left just starts to cool down. Like you take a pie out of the oven and put it on the counter, and any warmth you're getting from the pie is just it cooling down.
And so we're going to get to sit back and watch from another star system the white dwarf that was the sun slowly cooling off and slowly cooling off. And perhaps over several 100 billion years, perhaps over 1 trillion years, we're still working out the details of white dwarf cooling. The white dwarf is going to cool off such that it's the same temperature as the background radiation of the universe. It's just a rock. It's a really dense rock. It is perhaps the largest diamond known if it's a carbon white dwarf. Our sun's not going to become a solid carbon white dwarf, but it's just going to be this dead thing after enough time.
Right. They call that a black dwarf, right?
Yeah. Now, what's kind of cool, though, is for about 10,000 years, this hot white dwarf is going to be surrounded by beautiful nebula. Sort of think of the ring nebula. Our own sun could form a future ring nebula. And for about 10,000 years, that gas is going to be close in, glowing, beautifully lit up. Over time, though, it's going to float off, and eventually it will get consumed and recycled and used to make future generations of stars.
And what will happen to the planets?
Well, they're going to keep orbiting the white dwarf, and they're going to be sad and cold.
But would they be able to orbit the white dwarf forever? I mean, a billion years, 1 trillion years, I mean, is there some point where they have tiny interactions and they eventually just get flung out of the solar system or smashed into the star? Or...
The real question is, what are the future orbital interactions that our solar system is going to have with other stars? If our sun existed in complete isolation, where it was just our solar system and no other stars to interact with, then the much smaller sun could still hold on to the planets and everything would just orbit at a different distance. But because we do live in a galaxy with other stars, and our galaxy over time is going to get bigger as it collides with other galaxies and consumes their stars. And this leads to the potential for all sorts of interactions. And you could get perhaps a two-body interaction where two stars interact and their gravitational interactions fling some planets off, suck some planets in, perhaps exchange planets between the two stars. We don't know what angles, what masses, what velocities are going to be involved in these potential possible futures.
But time could be so long.
And time is so long that anything could happen. It's just a matter of what chooses to happen first.
Right. I mean, isn't it almost inevitable then, given enough time, if the universe has only been around for 13 billion years, 13.7, but if you look ahead 1 trillion years to the time that the sun has cooled down to a black dwarf, I mean, the chances of it keeping its planets must just be super remote.
It's not super remote.
Oh, really?
Simply because space is mostly empty.
Right.
The chances of it keeping all of its planets are somewhat lower. It's harder to hold on to Neptune and Uranus. They're just a lot further out. It's easier for them to get grabbed and yanked away. But the possibility of keeping things that stay closer in is a little bit more hopeful.
And don't we get another little glimmer of hope, because I know that planets have been seen forming around white dwarfs.
And that's exactly right. Planets have been found, and what's really cool is by studying where you find planets around other white dwarfs, it helps us understand what the possibilities of our own planet being consumed just might be. So while the future isn't hopeful if we stay in our solar system, um, at least we can look out and we can see, well, there's other white dwarfs that held on to their worlds. And so even if there's no life, there's still the romantic hope that our planet will exist.
Right, and I think then you have a much more stable situation. I mean, if you can survive and you can get to the right distance from your white dwarf, then you've got hundreds of billions of years to, sit around the slowly cooling down star, taking in whatever heat it's got to be able to give off.
And this is where the realm of science fiction starts to do some of the most fascinating story work. For instance, you can imagine a future where you take an asteroid, hollow it out, mount engines on it, and you fly to where it's safest to be, mount a wall of glass, and grow a great greenhouse inside this asteroid that you've turned into our new, very small home. And you can almost see yourself being able to manually keep that asteroid of humanity someplace that you're getting the right amount of thermal output from the sun. It's kind of bleak, it's kind of small and cramped, but it's possible.
Yeah, I mean, it's still kind of bleak. You're really grasping at straws here with what the future prospects are, and I think
I'm trying to leave hope for our listeners. I'm
no,
trying
know,
not to tell them that
I know.
humanity's toast in the next 10,000 years, even though it probably is.
Well, it's completely. I mean, I guess it's completely unrelated, but I think I get the impression there's this kind of psychological feeling that would be very exciting. That would be very groundbreaking and very, frontier discovery. But I think it would just be hard, and you'd wish there was just, air and rocks and
Yeah.
trees and the sun and oceans and just, all the stuff that just makes living possible, as opposed to having to scrabble for everything that you need to just not die. So
Right.
I think as you said, that is the best case of a terrible, inevitable scenario. We're kind of out of time now, but you know what the funny part is that I think this is the happy show.
Yes, the next one gets oh so much worse.
The next one gets really sad. So, well, thank you very much for taking us down this week's road, and I think we'll talk next week about how the universe itself ends. Really going to bring you down. So today we're going to look far forward into the distant future of the universe at timescales that we can barely comprehend. So when last we left our heroes, the solar system, the sun had turned into a white dwarf and was slowly cooling down. Maybe there were planets huddled around it. Yeah, and it would cool down for the next trillion years or so and turn into a black dwarf. But now we kind of need to rewind because things will happen to our neighborhood after the sun dies and turns into a white dwarf. So what is kind of the next major phase that happens?
Well, the universe and its destruction is a long and violent process. So perhaps the next thing that we look to as a major mile marker is the end of the Milky Way galaxy. We live in this nice, happy little, fairly, we think, pretty looking spiral galaxy with a bar in its center. We have the Magellanic Clouds off to the side, helping influence the shape of our system. But we're not always going to be this pretty little galaxy. In fact, we're on a collision course gravitationally with the Andromeda Galaxy. Our Milky Way is part of what we call the local group, a group of gravitationally bound together objects that we're going to be talking about a fair amount in this particular episode. And over time, gravity is going to cause us to interact with pretty much everything in the local group. And us and Andromeda are going to collide, probably light up our central supermassive black holes and send huge amounts of energy off into the universe.
Now, this is happening when astronomers look out into the universe. Everywhere they look, galaxies are moving quickly away from us.
Except for the local group.
Except for one. Right, except for the local group. And specifically, Andromeda is bearing down on us, right? Or we're bearing down on it.
Yes.
Now, when will we actually encounter Andromeda, and what will that look like?
It's going to happen probably in about 3 billion years, 5 billion years. It depends on who you're looking at, their papers. There's always a little bit of argument on when things are going to happen. And so our sun will still not be done being done. Our planet will probably be toast, as we talked about last episode. But our galaxy will start to collide with Andromeda while our sun is still going through its normal, happy little main sequence lifespan. And so our solar system will be around to watch the black hole in the center of the Milky Way lighting up, to watch our sky radically change as Andromeda gets bigger and bigger and bigger and fills the sky and then collides with the sky rather violently. So it's not that far in the future, which is kind of cool to think about.
And it's not going to happen overnight. The two galaxies will pass through each other and then move away, and then they'll come back together and do that a bunch of times until they merge.
We're actually going to go through a phase where we look a lot like the mice galaxies, the two little colliding galaxies that everyone's seen the Hubble pictures of a million times. And it's going to be a very pretty event for people sitting in other parts of the universe. And so that's really the next big thing we have to look forward to, is the destruction of the Milky Way galaxy and all galaxy life as we know it, or at least changing.
And once that process is done, and I think I'd read some of that research as well, that it's going to take 3 to 5 billion years to begin, but it won't be done for several billion years after that. It's sort of like it's thrashing, the two galaxies are thrashing around each other until finally it's just a ball of stars, right? We're just going to turn into an irregular...
We're just going to be another elliptical galaxy in the universe.
Right. And these are some of the largest galaxies out there, which have gone through many galaxy collisions and consumed a lot of stars. And they're mostly populated with the older stars, right?
A lot of the dust and gas that would otherwise go into forming new stars gets knocked out of the galaxy in the process, or gets churned into a final magnificent burst of star formation. So about the time that our sun is ending its main sequence life, our galaxy and Andromeda are probably going to be starting to end their final dance. And
what will happen to the black holes? Because I know there's supermassive black holes at the middle of both galaxies. Will they come together?
Very slowly. The galaxies, when we look out at other spiral galaxies that are in the process of merging together to form elliptical galaxies, we actually see two black holes embedded in the cores of these very dramatic systems. And we believe that over time, these smaller black holes will merge together to form larger and larger black holes. And actually, as we look out around the universe, one of the things that we notice is the size of the supermassive black holes in the center of galaxies is directly related to the dynamics of the spheroid of stars surrounding that supermassive black hole. So the larger that spheroid of stars, the larger the supermassive black hole. And in order to build that black hole, you have to have, in these collisions, the black holes merging. And that's going to give off a huge amount of energy when it happens.
Okay, so the galaxies have come together, and eventually the supermassive black holes have merged. What's next? This seems very stable. I guess we're going to run into other galaxies?
So over time, the entire local group, us, the Magellanic Clouds, Andromeda, the other smaller galaxies that hang out amongst us, it's all going to merge into a bigger and bigger system until eventually we're basically one giant island galaxy. And it's going to actually look like an island galaxy to us as well. The next, perhaps, big mile marker is when pretty much the rest of the universe disappears.
Whoa, what?
That's what it's just always fun to say. So our universe is expanding.
The universe is going to disappear.
Our universe is expanding, and we can only see so far. And as objects get redshifted further away from us, their light gets changed in color, and the energy gets stretched out, and eventually, as our universe expands, it's going to get to the point where the next closest object we can't see anymore. So,
right. I think we talked about this a bit, about how big the universe is, that the objects that are really, really far away are now or will be moving away from us so quickly that they appear to be moving faster than the speed of light, or they are traveling further away from us at faster than the speed of light. And that then and those galaxies, I think you said, will just fade away, that the photons that they're emitting will never reach us, and so they'll just, whatever photons are left we'll see, and then the galaxy will fade away. And then I guess you can imagine a sphere around the whatever we're going to call this new galaxy, closing inward of things that can no longer be seen, with the universe accelerating apart, and then eventually there's just us.
So the nearest other galaxy clusters, the nearest other galaxy groups are going to fade to red and red and red and further red and then fade away completely. So we're going to, over the course of billions of tens of billions of years, watch the universe fade to nothing.
Right. I know I've done several articles on this one, that Lawrence Krauss did a recent paper where they predicted that there would be a time when future cosmologists would have no way of knowing anything outside of our galaxy. And so there would be no concept of cosmology to understand that we are in an expanding universe that began with the Big Bang, because all of the evidence that we have today comes from the fact that we see the cosmic microwave background radiation, and that will disappear, and we see galaxies moving away from us, and that will no longer happen. Even, I think he said, even the abundance of hydrogen and helium, stars will have gone through so many generations and mixed everything up that astronomers won't even be able to figure that out anymore. So they will think they live in an eternal and unchanging universe.
What's even worse than that, they're going to think that they live in a universe that's gravitationally bound, and at some point is going to crunch in on itself. And it actually is going to return future cosmologists if they lose the history of the observations we're making today, which over 100 billion years, you have to kind of think, yeah, we're going to lose data. So back in the 1900s, like year 1900, we thought that our universe was only what we could see, only the galaxy, the stars, the Milky Way, and that Andromeda was a nebula or something out there. And there's this fear of, well, what if everything is gravitationally bound in such a way that it eventually collapses back in on itself? And all observational evidence is going to point in the far distant future to that also being the case of, well, we live in this island of stars, and on the distance scales that there'll be stuff to observe, they'll have no knowledge of dark energy. You have to be able to see other galaxies expanding away from you in order to measure dark energy. So we won't be able to measure that anymore. Their understanding is going to be limited by being stuck in this small, mundane island of what used to be a bunch of galaxies, and not being able to see everything out past the event horizon, everything out past the observable horizon. And it's sad to think that we're going to lose knowledge as we lose sight of the universe.
And it's quite amazing to think about the fact that we live at a really fortunate time. I mean, you think, oh, it's great to live when I do and where I do, but to know that in all of possible time, we happen to be at a point where cosmology is even possible, to get a pretty true sense of what the universe is doing, that will be lost to way future generations.
And that's just kind of sad.
Yeah. Well, we think we told people this would be the sad episode, and it gets worse. So, so at least, there you just like, what's outside our galaxy? I don't know. Okay, but then what's going to be then the future for the stars in the future galaxy and all of the stars in the universe?
Well, over time, they're going to run out of the ability to burn stuff. The planet Earth actually has the same problem at a certain level. Someday we're going to run out of fuel. Well, the universe is someday also going to run out of reasonably accessible fuel. Stars start burning by having hydrogen fuse in their core, having helium fuse next. You can't start off with a lump of carbon and get it burning, at least not easily. And eventually we're going to have burned up all the nebulas. We're going to have burned up all the dust clouds. everything that could easily be turned into a star and burned up is going to be burned up. And what's left over is going to be in the form of white dwarfs, is going to be in the form of, if you take a red dwarf star, it just sort of burns out and turns into charcoal. It's going to be left over in the form of neutron stars and black holes. We're going to have a bunch of stellar embers. And in about 100 trillion years, there's not going to be any stars that are actively burning via fusion processes things into higher elements.
So in about, was that 100 trillion years?
In about 100 trillion years.
In 100 trillion years, there will no longer be stars. So at that point, I guess the universe will be pretty dark. And I can imagine, right? You would start out with no more supernovae because you just can't get big stars anymore because there's just not enough concentration of material. And then you no longer have stars big enough to turn into neutron stars or even like main sequence stars. You just have every now and then a pocket of gas can collapse and you'll get a red dwarf or a brown dwarf. And then eventually there's not even enough material for red dwarfs. And then you're just waiting for all of the main sequence stars to turn into white dwarfs and then to turn into black dwarfs. And then you're waiting for all of the red dwarf stars to turn into black dwarfs. Then all the brown dwarfs just turn into black dwarfs. And then you've got a universe filled with black holes, neutron stars, and black dwarfs, right?
Yeah.
And planets, I guess, whatever there was left orbiting all of this dead material.
And one of the questions left for people who work on dynamics is, will eventually everything fall into a black hole?
That was going to be my next question. Yeah, you can imagine that over 100 trillion years, the chances of three-body interactions or stuff just decaying or things colliding and then it falling into the path of a black hole, I wonder what the chances are. Space is big.
Space is big, and I'd like to say that there'll always be some rogue planet shooting out between the black holes. There'll always be some rogue white dwarf that turns into a black dwarf as it cools off. There'll always be some rogue star shooting off between the black holes.
Last episode, we were hopeful for moving the Earth. We were hopeful for finding some way to sneak a planet around a white dwarf star and huddle up to the embers as it dies out. Now all we're hoping for is that some black dwarf doesn't get consumed by a black hole. That's it. That's the best we can hope for.
It's kind of sad where the expectation bar has gotten set in this episode.
It gets worse. But yeah, I know. I mean, it's funny. Like, oh, let's hope that some chunk of degenerate matter doesn't get gobbled up by a black hole.
Right.
Yeah.
But there are people out there working on this who say that in 10 to the 30 years, that's a 1 followed by 30 zeros years, pretty much everything is going to have fallen into a black hole.
And so you would get these momentary flashes, right? You get darkness everywhere you looked, and then every now and then something would fall into a black hole would flare up. You'd get like a mini quasar for a little while there, and then nothing.
And then nothing. And
right.
Then in about 10 to 30 years, even those flashes will stop.
Right. There'll be nothing left. Everything will be gobbled up.
Except for that little hopeful planet that I leave that's shooting off between all the black holes on a...
Yeah, that one where all our hopes and dreams are resting on. Is that one. Shooting off to a terrible future. So, to a bleak future that it can't escape. Okay, now let's imagine we looked at the Milky Way then, or the future version of the Milky Way. You'd have the supermassive black hole. Would it be orbited by other black holes, or would they all have just fallen into the supermassive black hole?
And this is one of the questions for people who work on dynamics. And if we have enough collisions going on, it could all end up being one giant black hole.
See, and once again, rooting for many black holes. But we're probably going to end up with one. So wherever there was a galaxy, one supermassive black hole.
But there's always the probability that you'll end up with just the right alignments of orbits, and you'll end up with a bunch of smaller black holes orbiting big black holes.
Yeah, our plucky black hole escaping doom, heading off into the universe to seek a terrible future. All right.
It's
All
all
right.
so
So then,
silly.
what's next?
Well, so once you've reached the stage where everything, except for this one little planet that we're all rooting for,
Yeah. No, oh, I guess we also have to mention that dark energy has been accelerating the expansion of the universe for 100 trillion years.
yeah. And so there's nothing that you can see outside of our galaxy.
There's nothing. I mean, to say that things are far apart is an understatement. There is
Basically, the universe is expanding faster than something can go.
right,
So
and so there's nothing. There's no way that anything can reach anything else.
yeah, it's just not going to happen. It's that whole the
Right.
graph paper is expanding faster than you can draw.
Right. Okay. So then we've got our black holes,
Now the problem with black holes is they evaporate given enough time.
and we will give them time.
And we're going to give them a lot of time. And so at a certain level, once you have a big black hole, the cosmic microwave background is filling it with energy faster than it's evaporating. But in about 100 billion years, even the cosmic microwave background is going to get redshifted to the point that it's fairly meaningless. It's going to end up with a wavelength of about 1 meter, and that's a frequency of about 300 megahertz. And the amount of energy that it's carrying is going to be 12 orders of magnitude less than what we currently experience. So its ability to keep those black holes going is going to be vastly diminished. And it's just going to keep getting worse.
So right now, the only thing that will be keeping these supermassive black holes their current size is this trickle of radiation coming from the cosmic microwave background radiation, I guess errant photons that somehow make it, the occasional particles of interstellar dust that fall into it keep the black hole in stability. But I guess eventually there will be a point where not even that material is reaching the black hole and it starts to decay.
Yeah. And so these black holes are evaporating. And the small ones go first. And they sort of pop off into nothingness.
See, so our plucky black hole that thought it escaped destruction
Dies first.
is the first to die.
Yes.
Because it's smaller, doesn't have the mass, and so it will evaporate.
Yeah.
And we've done a whole episode or we did a question show on how black holes evaporate, so
Check it
I
out.
won't go into that this episode.
So even the big ones, they're not going to last forever. Here's where you take your Google number. It's a number. It's a 1 followed by 100 zeros. You take your 1 followed by 100 zeros, place the unit years after it, and that's when even the black holes have evaporated. And our universe is basically nothing more than these low energy photons forming background radiation. Everything is cool, cold.
I can imagine these particles coming off of black holes one at a time getting swept up in dark energy and being accelerated away from the black hole, right? Because they're no longer, because they've been able to escape from the black hole, they're not necessarily gravitationally bound to it anymore. So they're just going to start escaping away.
But it's not so much that they're escaping away as they're getting stretched out.
Right.
So as this photon tries to fly across the universe is expanding. And what might have started off as a high energy blue photon is going to become red, become infrared, become radio, become no useful amount of energy at all.
Right. A state of energy, a wavelength that could be measured in light years, right?
And so we're looking at a universe where someday in the future, basically everything sits as close to absolute zero as atoms can get. I mean, imagine the entire universe basically becoming a Bose-Einstein condensate. What a cold, scary place to be. The thing is, all energy, all mass, it's going to be conserved. The amount of mass and energy our universe started with, it'll still have it. But the volume it's spread out over, it's basically all this wonderful stuff that makes up you, me, our desks, our table, our planet is going to get spread out so much that it's as though everything were the deepest vacuum you could ever imagine.
And what then?
And then it's essentially over. It's energy death. The universe just hangs out being cold.
I mean, it's not hanging out. It's accelerating.
Well, yeah, it's accelerating itself apart, but
Yeah.
but there's nothing there. And
Right.
so it's a very sad, cold place to think about. And then there's always the question of, well, what if our universe shreds itself apart and shreds itself into other dimensions? But that's where we start getting completely out of all observational, conceptual ideas and into the land of scary math.
And that is the same thing as people hoping that we can, huddle up next to that white dwarf, that we can prevent the Earth being consumed by the sun as it turns into a red giant. I mean, it's this hope against all hope that there's a way to avoid the final heat death of the universe.
And this is
heat death
why
sort
we
of a
read
weird,
sci-fi.
which is why I read science fiction, and you have some future astrophysicist come up with a portal to another dimension and head off to that other dimension, which will probably also end in a heat death. But
Yes.
you're killing
Unless we tunnel to a third or a fourth, or just
right. Or but I think a lot of this thinking of like, well, what if there's multiple big bangs, and what if they happen, regularly or whatever, and a lot of this is driven by the awful conclusion that that's the future that our universe faces. That far, 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 far down in the future, beyond our lives, the universe is essentially a rapidly expanding place of nothing. That all that came before is gone. And that's too bad. That's really sad. But
we don't want to be erased.
we don't want to be erased. And that's what I think what it means. And that's why even putting our hopes and dreams into that black dwarf floating away is a way to say, we were there. That was us.
Yeah.
So, and that's, I think, all we got for this week. Next week, it'll be about puppies and flowers and really wonderful, hopeful things.
Or at least about the Hubble Space Telescope.
Or the Hubble Space Telescope. Yeah, I think that's what we're going to do. All right. Well, have a good trip, Pamela, and we'll talk to you next week.
Okay, sounds great, Fraser. Talk to you later.